Greetings again. Now in the second installment of my video session for the second week, I'm going to talk about machine programming. So this is the soft side of VESP 1.0. We're going to look at programming, machine programming as it is called, as opposed to the hardware aspect, which was basically the sequential circuits that we designed to describe the operations of a von Neumann architecture, which was our VESP 1.0. Now, so these are the 8 instructions of VESP 1.0, and the particular instructions that I'm really going to focus on are these two, load instruction and the move instruction. Of course, we're going to use the jump and the jump if 0, as well as the add and the complement instructions, and the end also halt. But the key focus would be here on the move instruction. Especially, we're going to talk about what's something called self-modifying code. So, just to recap, the load instruction basically allows us to load constants into memory, and those locations, of course, include our specialized registers A and B. And then the move instruction just moves these operands around from one location to another. And so we did this example in class last Wednesday, and the example basically takes an array of values, which in this example happen to be 10 in quantity, and then adds them up together to come up with a sum. And the sum, of course, is initialized to 0. Now, locations A and B are locations 0 and B in our memory are permanently dedicated or assigned to these two specialized registers of ours, A and B. In addition to those, we will need in this example 2 more locations, and location 2 is what we will call our virtual index register. This is not to be confused with the actual index register that we just learned on Monday when we looked at VESP 2.0, and location 3, which will be the place where we're going to keep our sum. So now these steps here just summarize our algorithm, the program that we want to write. The first step is to load the array, the elements of the array, into memory. The second step will be to initialize the sum to 0, so we could start with 0 instead of like some arbitrary number. And then initialize our index to location 10, which I decided to store the first element in my array in this example, and then sort of like ease our way into the loop by checking this virtual index register to see if its value is actually exceeded the location that just goes just behind the array on the other side of the array. So that location happens to be in hexadecimal location 14, as we shall just see. And then once we decide that we're not going to exit because we have gone past the array, the last element of the array, then we go out and enter the loop, and then we go out and do the addition itself, and then of course we will introduce at this point in time, because we don't really have a direct indexing mechanism, we're going to do what we call self-modifying code version of indexing. And then, of course, we'll update the index as we come out of the loop, and then go back to step 4. That is to say, we repeat the same question to see if we should really exit. If we didn't update the index by incrementing it by 1, then we will never be able to exit this loop. So in the first part of the code, I simply load the values of my array into locations starting at A and running up to location 13. This is hexadecimal. And so all these numbers have been created so that we can add them. Now, I've done something slightly more particular. I've actually picked these numbers to be 1, 2, 3, 4, 5, all the way up to A, so that I can add these first 10 numbers easily in my head. 10 times 11 over 2, which is 55, and I could easily then test my program to see if it actually computed me the right number. That's why I've done this. All these instructions are loads, as you can see. load to location A, load to location B, to C, to D, etc., all the way up to location hexadecimal 13. Excuse me. Now, in this next part, I am just clearing or setting the index to the first location in the array, which is location A. That is the index register right there. I'm actually loading this constant into that location. And then after that, I clear the sum. I put a 0 into location 3. Now that I've done this, I go out and check if the index has actually exceeded 14, which is the location right after the upper bound of the array. Now, of course, I just initialize it to let's say hexadecimal A, so I don't expect it to be 14. But that will happen as I get back to this point down, once I get through this loop and then come back here. But this whole process is just to test to see if the virtual index location that we created has actually gotten something that is like 0 in it. So we put the 14 into the accumulator, we complement it, we then put the running index in that location 2 into register B, we add the 2, we then actually add 1 to the sum because we're doing 2's complement addition, and then we do the addition, and if that is equal to 0, this is like jump if equal to 0, then we jump to location 53. Now I don't ordinarily know this as I write the code, but since I completed this code, I know where it is, and that's why I put this in parentheses. So that is just the index check. This is all it does. Now once we get past this point, we now enter the loop itself. So in the loop, we begin by modifying. This is where the term self-modifying code comes from. By modifying the location where the address of the move instruction is that move instruction that's going to move the current element in the array into register B is located, and that happens to be location 45. So here I lined up 2 move commands, if you can see, 2 move instructions, one there and one there. The first one simply alters the address portion of the second move instruction, which does the actual moving of the array, the element, the current element, into location B, where I'm going to use that second operand together with the first operand in the A register to compute my running sum. So I put that into B by way of this step, these 2 move instructions. Now keep in mind that this move instruction is executed before this, so the address, which I left as XXX's, but then I filled them with zeros because I got to write something in there. So by the time we get to this move instruction, this place has been altered by this move instruction, and of course its contents come from our so-called virtual index register. And that's how I modify this. Now once I do this, I put the sum into A, and I add the 2, and I save the sum. I'm done with my addition. The next thing that I should do, the last thing really, is to increment the IX, or not IX, but the virtual I index location, and then go back to the loop. So that's what I do here. I copy I into A, that's what I do here, and I put 1 into B, and I add the 2, and I save it back into I here. I just didn't write the code. Let me actually write that code in there. So that code would be here. It's 3002, and that must be 000 right there. That takes care of that. And then, after that I loop back. Of course, this is the location where we come to halt. That we would jump from this location here, this instruction, and that I just put it in here. Okay. So now this is really what the program is, but let's see how this really works, or it doesn't work for real. So I go to my copy of Xcode, and this is the second version, BESP 2.0. The only reason I'm using this is I created this code and I saved it into a file, so I'm going to open it from there. This will also be an illustration of how you do this. So I'm going to run this. I'm going to stop when it's running, and I'm going to start out fresh. So now I'm going to start and just put 0 to enter my program, and I'm going to load the program to location 020, and I'm going to enter it from a file, and I believe I call this file, what did I call it here? So it goes vesp6.vesp, temp6.vesp rather. I'm going to put that in, and then I'll say, don't save this because I just created this myself. And this is my program, basically. This is what it is. Now, so let me actually copy this because I'll just email this after this demonstration to you. You could also copy and then email it to you directly. Maybe I do that. But now let me just go ahead and execute this. So execute it. Okay. And I'll go for long trace. So let's see. Go long trace. So the program halted, stopped. So you can see the last instruction is halted. Executed a bunch of instructions in between. What I'm really interested in at this point in time, you can debug your own code if you like, would be to look at the location number 3 to see if I actually happen to have 55 in there. So I'm going to just say, look at location, just take a look at locations maybe A through 3, right there. So there it is. My last location, this is the one I looked at, is 37. That's an hexadecimal. 3 times 16 is 48, plus 7 is 55. So the program worked, okay? And so I'm going to actually take this code and I'm going to send it to you just like this. I'm going to copy this from here. I'm going to go to my email and I'm going to say new email. Just say new and ENEE350. Okay, so everybody will get a copy of this sample code. Or just say self-modifying code example. Just put a hyphen in there so that you don't get that typo. Okay. So if you can just take a look at this, I'm just going to paste it down. That's your code right there, the one that I just ran. Okay. So you have that. I'm going to send it to you, to everyone in class, Spring 14. There it comes to you. All right. And now I'm going to basically go back to my PowerPoint presentation here and then complete my discussion. So that was just that. And now here's the summary. In a way, we covered the decode and execution process in VESP 1.0 sequencer and showed how it can be converted to a sequential circuit. Let's put the full stop in there. And then really briefly, we showed how an array of elements can be indexed using a self-modifying code. That was what we did. We added numbers. Now here's the second assignment, so it's really programming still, but also a little bit of logic design. So in the first part of the second homework assignment, you're going to specify the logic for the data input for the ith flip-flop in the MAR register for VESP 1.0. I've done the example for A, so I ask you to do this for MAR. And then in the second problem, I'm just asking you to go ahead and do this expression here using self-modifying code. And I've written down here where the locations are, where these arrays are supposed to be stored. And of course, the third part of the problem would be to actually write the code, try it out, and to see if your program, to verify that in fact it works. In other words, you test your programs. Now, actually what I'm saying here is that you also want to write a program. This is what I'm asking you to do, to store the numbers 1 through 100 in X and Y, and then combine this second program with the one that you've written in this second problem to test both your programs. I don't want you to write 100 load instructions, just write a loop where you can increment something and then store it into these consecutive locations. So I'm trying to simplify your work here. All right, I think this is the last slide and I'm kind of done. So I'll see you all in class tomorrow afternoon. Until then, have a great evening. and I'll just upload this particular video along with the first one so that you can all view this.